Hi and welcome to this series for numerical analysis for TCEM 2101. So we'd like to continue on what was said in the previous lecture, or in the previous video rather, by making some more other important introductory remarks. Okay, so we are still with our introduction, but I would like to make some more introductory remarks. Okay, as I mentioned earlier, that solving mathematical equations is an important requirement in this field of engineering. Okay, however, like I said, that some of these problems are really hard. They are either very difficult to solve or do not have analytical solutions. So we resort to numerical methods, which looks at ways of exploring the techniques that can give rise to approximate solutions. Okay, so under here the keyword is that we are looking for approximate solutions. Okay, now if you're looking for approximate solutions, one can wonder to what degree or how close, let's say, since it is not the true solution, not the exact solution, let us use the right word. It is not the exact solution, it is just an approximate solution. So one can wonder how close is the approximate solution, how close is the approximate solution to the exact solution. Okay, that will be a very important question which we shall look at here in numerical analysis. Okay, that brings rise to the concept of errors. Okay, and what are we going to say an error is? We are going to say that an error is the difference, okay, is the difference between the exact solution and the approximate solution. Or let us say that the exact solution is equal to the true, no, let us put it this way around. Let us say that the approximate solution, okay, approximate solution equals to the exact solution plus the error we make, okay, in whatever method we are using. So the goal of numerical analysis here is to try to make this error as small as possible. Okay, we want to make this error as small as possible, approach to zero, so that the approximate solution is, you make the error as small as you can. You make it as close as it is to zero, so that you have a really good approximation to the exact solution. Okay, so well, that brings us to another term which we would like to talk about, and that is the relative error. Now, the relative error, we are just going to compute it as let us call it R. Let us take it in terms of its magnitude. It's going to be given by, the error here, the magnitude of the error, and by, since we said it is the exact, you divide by the exact solution. Okay, this is what we are going to term as our relative error. Okay, now I mentioned earlier on also that in this area there are lots of numerical tools, okay, which are being used. Okay, so these numerical tools are applied on computers. Okay, so let us say these computer-based solutions, because we are in the real world. We are not doing these things by just pen and paper or finding numerical solutions using pen and paper. No, we are going to use the help of computing power to solve some of these equations numerically. Now, I would like to mention a few other remarks here about the steps which are involved in using, these to obtain this computer-based solution. One, there is the aspect of the modeling, that is the mathematical modeling, okay, coming up with the mathematical equation, okay, maybe it is an ordinary differential equation, or maybe it is a partial differential equation, and so on, something which is going to represent a physical process, okay. And then two, when we have our mathematical equation mainly written in the form of an ODE or a PDE or whatever it is, then we have to select or choose an appropriate numerical method. Appropriate, not approximate. Appropriate numerical method, okay. Now, of course, our course we are studying here is by no means exhaustive. However, many of these numerical methods have their characteristics, that maybe this numerical methods works for these kinds of problems, it does not work for this kind of problems, it works in such conditions, or when these conditions are lacking it will not work, and so on and so on. So this is a really huge area of applied mathematics, but what we are getting here is just the basics or the ideas. So yeah, for those of you who are really interested, you will study these things more in detail, maybe if you pursue other advanced courses. So when we choose an appropriate numerical method, we get our numerical method. In technical terms, these numerical methods, they say, okay, I don't want to use the terms here, but okay, we can discretize. They call it discretize. We discretize our equations using these numerical methods, and then we come up with something which you can write in a computer language, that is the programming. And then lastly, you do the simulations or the executions, okay. You run your code or you execute it, and then you can visualize it, and then visualize, and maybe you can make any interpretation of results, okay, and so on. So this is its logical steps. You do the modeling, then the numerical method, then the programming, then the simulations, and the visualization. So our focus is mainly here. All the problems we are going to look at, we are going to be problems for which the equations already exist, and then our focus is mainly going to be here, looking at these numerical methods, although we shall have some slight work in here, something very small, just for the curious mind, okay. Alright, now I'd like to finalize these remarks here by, since we mentioned errors, so there are types of errors, okay. Of course, there are those that we make, okay, what can I say? Okay, let us start with the ones which are inherent errors or experimental errors, okay. Those that are inherent or experimental errors. Alright, okay, now these arise due to the assumptions made in the mathematical modeling of the problem. Of course, it is sometimes very difficult to express reality or a physical phenomenon exactly in terms of mathematical equations. You make some assumptions here and there. So in the process of making assumptions here and there, of course, there are some errors which will come about, okay. Then two, we have those that are called truncation errors, okay, the truncation errors, okay. Now these are the ones that correspond to the numerical technique which we are using, okay, because we shall later on see maybe some of these are derived using Taylor series expansions, okay, and then maybe as you are deriving some of these methods using the Taylor series expansions, you reach somewhere and then you have to drop some terms, some higher order terms, maybe by assuming that these terms are negligible. Okay, negligible, that maybe the error that occurs by dropping some of these terms is not significant. Well, sometimes, okay, someone can say it is not significant, others will argue that, hey, maybe they are significant, and so on. So in the process of doing that, dropping some terms here and there, those are called truncation errors. And then we have the round of errors, of course. Round of errors, these ones mainly result in the way maybe the computer stores the values. Of course, there are different ways of storing values. Some are stored in terms of integers, or some are stored in terms of floating point, and then some others store them in terms of fixed point, and so on. You know, there are round of errors. The computer is not going to give you like pi for everything. You reach somewhere and then you cut off. Maybe this is how it represents it, maybe to a number of significant figures or to a number of decimal places, and so on. So all those values that are dropped due to these round of errors also, you know, contribute to the errors we have here. So the thing in numerical analysis here is that we try to make methods or come up with methods that minimize these errors, the ones that are inherent, truncation, round off, and so on. Whenever the errors are really minimized, then we have a really good approximation to the exact solution. Alright, okay, thank you so much, and see you in the next video.